welcome you all to this lecture on conditional GAN to synthesize OCTA images from the fundus images. Actually, we are myself, Dr. Raja from Veltech University, and Dr. Sambat Kumar from my Veltech University and EC department. We are participating in the IEEES Generative AI Hackathon, where we are developing generative AI based application to synthesize OCTA images from fundus images. So I would like to show you the sample of OCT and the fundus images. So these are the fundus images. Those who are having the background on medical image processing might be knowing these are the fundus images, a very simple imaging modality. Modality is OCTA, as we can see in the screen. Fundus and the corresponding OCTA, taking the anatomy, same anatomy, and acquiring the images of the same anatomy. Fundus being a cheaper imaging modality where we can see the optic disc and blood vessels, uh, a shallow vision of the blood vessels we can see. Whereas when we go for the OCTA, it is an advanced imaging modality where we can see the depth resolved blood vessel maps. Actually, it eliminates all the other anatomies. So when I discussed with the doctor, he told that both hold complementary information in diagnosing diseases like diabetic retinopathy and age-related macular degeneration. So our idea, so far, doctors have been using fundus mainly for diabetic retinopathy diagnosis, and if they want additional information, they can go. The highly developed hospitals, they will be having the OCTA imaging modality. The cost being 20 lakhs, around 25 lakhs. Whereas the fundus image, if you see fundus camera, if you see the cost of the device is around 3 to 4 lakhs. Okay, so we are exploiting the computational power of generative AI, where we are training the generative adversarial networks with OCTA and fundus paired images, and we are trying to synthesize OCTA images for newly acquired fundus images. So that is what our project is. So we know the power of generative AI. So with the power of generative AI, instead of generating specific images, we are trying to generate paired images. Not exactly generating paired images. If we give one modality, we should be able to generate another modality. Already there have been some projects successfully completed with synthesis of CT images from MRI images or MRI images from CT images. So these are going to be benchmarking in the future, where we can expect the hospitals to have only one imaging modality where they will be able to generate the further modalities without the availability of the second device itself. Okay, so that's what one of the projects we have taken, and we have gone to the extent of developing a user-friendly app. We are running the code in Python, whereas when we go to the doctors, they cannot run the Python code and all. So we are trying to develop. We have developed a user-friendly software application, not in public domain, in local host. We are to that level. We have completing this paper, where myself and Dr. Sambat Kumar have worked in different parts of this particular project. We being completely with engineering background, the medical inputs are given by Dr. Kaushik from Vasan Eye Care, and of course, Ishuru Srinajira is our project mentor from the IEEE hackathon side. So we are working as a team, and we are very happily developing the project of synthesis of OCTA images from fundus images. They are given here, and the generator of the particular conditional GAN is a unit. So this entire block was done by Dr. Sampat Kumar, the coding part, and we have made some novelty also, like using entropy based thresholding. So when we want to preserve the blood vessels, I have thought like entropy will be the perfect parameter to preserve the blood vessels, and that have given suitable outcomes also. Okay, so this is the entropy of the actual image, entropy of a small portion taken from a small portion of the image, a tile of an image, where the entropy is 7.6. If we go for a general GAN, how much it is preserving, and our GAN, that is blood vessel adversarial loss we have defined. Based on that loss, we are able to much better preserve the finer blood vessel details. We call it as the doctors call it as a microvasculature. As we have the input data in the drive, we are loading the data from the drive, that is original fundus images, and what needs to be synthesized to train the GAN, mapping the images from one modality to next modality. One is mapped to one here. So fundus images mapped to the OCTA. Those training are being done. Okay, so we have divided the data set is already available on the internet. The data set is not developed by us. So we have the train A, train B, test A, and test B folders, and those are being called from the particular Google notebook. And coming to the data pipeline, we are having the data pipeline here: a train A, train B, as I have shown here, train A, train B, and all are here there in my Google Drive. And from there, I am taking to train A directory, train B directory. So train A will be the training fundus images, and train B will be the training OCTA images. That has to be paired and learned. For this fundus, this is the OCTA. Likewise, it has to pair and learn. And it have a GAN architecture with the generator and discriminator. That's what we are describing in the code here. We are describing the generator and the discriminator at this part of the code. Clear, I am going to concentrate only on generator underscore G and discriminator underscore Y, because that is only related to the project. Underscore G, it generates OCTA images, and discriminator underscore Y. So what should the discriminator do? As per the explanation in theory part, discriminator should be able to discriminate between the synthesized OCTA images and the original OCTA images. So generator loss. What is a generator loss? Is nothing but TensorFlow dots ones like generator. So what this TensorFlow dot ones like will do is it will generate a tensor of ones that is equal in size to this generated image. Yeah. First we'll discuss the discriminator loss. What is the discriminator loss is done is for real images we have ones. We have ones compared to the real images, and we have zeros generated for the generated images. So the real images are labeled as ones and the synthesized images are labeled as zeros. So whenever there is a mismatch, there will be a loss function. So both the terms are being added here. So total disk loss, that is being the discriminator loss. And when we come to the generator loss, here we are actually fooling the generator. So generator in the sense it is a synthesized image. So synthesized image should be taken as zeros. But we are putting a ones. We are putting as ones. So what happens is initially the generator loss will become very high. So after a certain period of time, to reduce the generator loss, what it will do is the generator will start synthesizing images that will look as good as the original images. So finally, we are running the code that is the generate underscore images, generate underscore G for sample fundus. Sample fundus, one fundus image we are taking, and that we are giving as an input to the generator underscore G, and how the image is being predicted is shown here. And this is the original image, and this is a predicted image done by our algorithm, and we have taken several images and we have estimated the mean square error also. Okay, so this is the original fundus image and this is a predicted image by our algorithm, whereas this is a ground truth is being taken from test underscore B. So train B, like train B, we have test B. So this is the ground truth, and this much our algorithm is able to identify. And what is the difference in the prediction? That is estimated as a mean square error. 0.17 is a mean square error. In that case, our algorithm is able to replicate up to 83 percentage. It is able to replicate the synthesized OCTA images. Since we have the ground.
So with the help of that CGAN, so here we have developed a front end. So the same thing only we are going to give it to doctor. So in a local machine. So this is developed by the Flask framework. So this is the same as our blocks, necessary blocks what we have developed. So instant normalization as well as that customized SC block. After that, we have called that unit also. Then after trained, so here we are going to, that is after the training, so we have saved our model. So the same model here we have called. So here you see, so this is our model we have saved, then the same model only we have given here, so that whenever we are going to see in a local host, so that we are going to upload an image, then we will get a corresponding OCTA synthetic images, so which is developed with the help of Flask. So this is that necessary files. Then here we are going to call whenever it is displaying IP ID, so that we can able to upload an image, the corresponding synthetic images we can able to see. So this is the IP address. We are going to copy and paste it in our browser. So this is an app which is created by ourselves. So this is the IP address link. So here this is our web page. So here you see, click or drag and drop to upload one image. So the namely fundus image. So I'm going to upload one fundus image. So I've already uploaded. So after that we need to generate the corresponding OCTA image. So here you see, so that I'm going to click the same, upload and generate. So this is our image, synthetic OCTA image for the corresponding OCTA image. So if suppose we need to download the image, means we have an option here. So to download the same. So with the help of that, doctor can check the corresponding OCTA path image from the fundus itself.